Good morning, algebra friends. I've been studying some more geometric algebra, and it just keeps getting weirder. I love it. I want to talk about the relationship between the geometric product and the complex numbers. Now, this has been done on YouTube. There's many examples of this. The ones I watched, they just flew through it like it's the most normal thing in the world. It's not. It's not the most normal thing I've ever seen. It's really rather odd. Okay, the geometric product, we've seen this before, is defined as the product of vector A with B is the inner product of A and B with the outer product of A and B. So it's A dot B plus A wedge B. This in itself is not normal to me. I'm getting used to it though. It can also be written like this: the magnitude of A, magnitude of B, times the cosine of the angle between them plus the sine of the angle between them times this bivector. So all of this times these magnitudes. Now, where in the heck did all this come from? Well, let's break it down one piece at a time. Let's just do some basic review stuff I know you've seen before. The dot product. Where did this guy come from? Okay, so we got a vector A at 3, 1. We got a vector V at 1, 2. There's an angle between them. We're going to call theta. Okay, so the dot product of B and A is actually the projection of B onto A. So if I drop a line the segment here that forms a 90 degrees angle with A, this length here, which I'm going to call the projection of B, BP, this length times the magnitude of A is actually the dot, the product, right? So how can we find this length BP? Well, look at this. The cosine of theta is equal to the adjacent, this piece, divided by the hypotenuse, right? So let's go back to our doc and look at that. Okay, so we said that the cosine of the angle, the theta, was equal to the adjacent, which was that projection, divided by the hypotenuse, which is the magnitude of B. So we take this to the other side. We said the product is equal to the magnitude of vector A times that projection, the piece, which we now have an expression for. So we plug that in, we get A dot B equals AB cosine theta, which is the well-known expression, okay? So let's do the same analysis to the wedge product. Okay, so here's my two vectors, A and B, and I want to find the wedge, the product. And the way I do it is I add them together first. So I got A plus B or B plus A, it doesn't matter. Then I go tip to tip with a line, the segment. Then I go tip to tip with this line, this segment, and that forms my parallelogram. So now I have A wedge B, you go in this direction, and that forms a counterclockwise rotation, which makes this a positive bivector. Okay. So now if I drop that same lines, this segment, there it is, here, and I call that line segment H, another definition of the area of this parallelogram is the base times the height. Well, that is the height. But how can we find out what it is? Well, what is the sine of theta? It is the opposite over the hypotenuse. So the sine of theta is equal to h over the magnitude of b, right? Let's look at that. Okay, so we said the area of the parallelogram is the base times the height. Well, the sine of theta was equal to that height divided by the magnitude of b. We take that to the other side. Now we have an expression for height. And we know what the base was. It was the magnitude of A. So we put all that together and we get this expression, but we still have to include this bivector, right? Because this is a wedge, the product. So it's not just A, B, sine theta. You have to include the wedge, the product, the bivector. All right. So now we got these expressions. We put them all together. We factor out the magnitude of A, magnitude B, and we get this, which is starting to look very familiar. All right. So let's do a quick review of these orthonormal basis vectors in geometric product. So the geometric product of E1, E1 is E1 dot E1 plus E1 wedge E1. Well, remember now, these are orthonormal, which means they're unit length 1, and these two are on top of each other, so the cosine of their angle is 0. Cosine of 0 is 1. So that just becomes 1. Any vector wedged with itself is 0. That's one of the rules. So we just get this. And by the same logic, E2, E2 is 1. Now, what about the mixed one, E1, E2? Well, E1 dot E2, what's that? Well, they're orthonormal. So the angle between them is 90 degrees. What's the cosine of 90 degrees? 0. This drops out. So we're just left with E1 wedge E2. So anytime you see E1 wedge E2, you can write it as E1 E2. But here's the interesting part. What if we square this? What is E1 E2 squared? We can write it like this: E1 E2, E1 E2. We can swap these two, right? So we can go 1 1. We have to pick up a negative when we swap. E1 1 2 2. 1 and 1 is 1. E2 times E2 is 1, so we get a negative 1. What if I take the square root of both sides? Oh. So E1, E2 is equal to the square root of a negative 1, which is what? Imaginary number. And I'm just going to call it capital I because it's similar to I, but it's not exactly I. It's so weird. I love this stuff. Okay, so now that we know this, we can rewrite this equation, just E1 wedge E2 is E1 wedge 2, or we can just put an I in there. And I'm still not going to call it I. All right, now what's the difference between big I and the one you're used to seeing in complex the numbers? Well, the first thing let's do is let's go multiply out some complex numbers by I. So I'm going to multiply I from the left like this and also from the right. Let's go look at that. Okay, so this is the real number line, the imaginary number line, and I've plotted a line segment vector, whatever you want to call it, which is 3 and plus 1I. Okay? Now, I'm going to hit that from the left with another I. All right, what's going to happen? Okay, we got a rotation, and we knew we would. So it went in the counterclockwise the direction by 90 degrees. All right, now I'm going to hit it here from the left with I. So I did it from the, I did it from the left. Now I'm going to do it from the right. What do I get? I get the same thing. And we knew that would happen. So, and why did I do this? I'll show you right now. Okay, so here's my vector 3, 1. Now I'm going to multiply this vector from the left with the bivector E1, E2. Oops, what do we do here? We got a rotation clockwise by 90 degrees. Now let's multiply that same vector from the right by E1, E2. Oops, now what happened? We got a rotation counterclockwise by 90 degrees. So from the left, it went this way by 90 degrees, and from the right, it went that way by 90 degrees. So that is the huge difference between a bivector and a complex number. So let's go look at that on the doc. Okay, so here's where we were. So we did this already. We multiplied I times a complex number from the left and from the right. Obviously, we get the same answer, and we knew we would. Now, when I did that vector 3, 1 from the left, you can see what happens. You can pull these scalars out, by the way. So you get 1, 2, 1 and 1, 2, 2. Now, the 2, 2 is going to give me a 1. But this one, I can flip these, right? And when I flip them like this to a 1, 1, 2, I get a negative. So I wound up with a 1E1 minus 3E2. Now, when I multiply it from the right, like this, I get a 1, 1, 2 and a 2, 1, 2. So it's basically the opposite of what I just did. And I get a negative 3E1 plus 1, 1, E2. So that's the big difference, really, between trying to treat this bivector E1, E2 as a complex number. It kind of is, but it really depends upon which direction you multiply it from. Anyway, I thought that's fun. I'll see you later.